Over the last few hundred years, humans have had a tremendous impact on the planet Earth. As a part-time historian, I would say we really need to extend this back about 14,500 years ago. This is a time in eastern Syria when people began to live in the same place year-round, a place called Abu Huraira, a small village. This is when people began the lifestyle of farming, agriculture. Again, around 14,500 years ago, people began to modify plants. They were starting to modify animals, choosing animals that weren't particularly athletic and intelligent and dangerous, like sheep, as natural first domesticates. Subsequently, the rate of these changes has increased dramatically, exponentially in the recent, and this poses a serious threat to the Earth's systems, including biodiversity. Significant changes in how we use land and the resources that we require are necessary to slow or prevent future changes. This is what's loosely known as sustainability. The problem with sustainability is we're not really sustaining the natural world, we're sustaining our activity in that world. So it vaguely benefits nature, but in reality, it's more geared towards benefiting us, the sustainability idea. In this lecture, we're going to talk about the rise of carbon dioxide in the atmosphere, how it was defined by the Keeling curve in a particularly no-nonsense manner. We'll discuss types of anthropogenic global change, the things that we've done to change the Earth. We'll discuss climate change, ocean acidification, its implications for the future of the Earth, loss of biodiversity, the implications, again, for the future of the natural world, and just for the future of having an interesting place to live. And then we'll wrap things up with managing the carbon crisis. Is there a way to get a handle on what we're doing wrong now, slow that damage, and potentially even begin to reverse it? High hopes, but technology is improving. If more people have a concern related to this issue, it becomes more important to the rest of the world. Starting off with the rise of carbon dioxide in the atmosphere, the Keeling curve represents measurements of atmospheric CO2 that were taken over Mauna Loa in Hawaii. This is on the Big Island of Hawaii. There are two peaks that are nearly the same height. Mauna Loa, which has the meteorological observatory on it, and Mauna Kea, which has the main astronomical observatory located there. And if you were to pivot from looking this direction at this summit to the opposite direction, you would see Mauna Kea sticking above the clouds. The reason we choose Hawaii, or Keeling chose Hawaii, is that the samples that are tested represent uncontaminated air, uncontaminated by local fossil fuel emissions. There's not a whole lot of big industry on Hawaii, so we would anticipate little local effect, which is what we see. Also, it gives us a global average CO2. We're in the middle of the Pacific Ocean, the biggest ocean on Earth, the biggest open space on Earth. Therefore, it gives us a good global average of CO2 in the atmosphere in a global context. Keeling's observations provided evidence that CO2 is increasing in the atmosphere. Unequivocal evidence. It's unarguable. It was demonstrated that the change could not be from natural sources, and the increases were not the result of seasonal fluctuations, although the seasonal fluctuations show up very, very clearly in the record. And it's one of the more interesting aspects of the record, I think. And here we have an image of Dr. Keeling receiving the National Medal of Science from former President George W. Bush for his efforts to measure CO2 at Mauna Loa. Over the last 62 years, the Keeling record has demonstrated a 32% increase in carbon dioxide in the atmosphere. This Mauna Loa observatory record of CO2 over the last 70 years or so is pretty consistent in its recording of the increase of CO2 in the atmosphere. We see seasonal rises and falls that are related to the leafing and de-leafing of plants in the northern hemisphere. That's very consistent throughout the record. And again, the rise of CO2 is very consistent. It's very accurately recorded, so we can be pretty sure this is exactly the amount of CO2 in the atmosphere at any given time over the islands of Hawaii. When we look further back in time, we need to go beyond the instrumental record to the physical record. And there are a couple different ways to do this. In this case, It's the simplest way, technically, in that we're taking CO2 out of bubbles from ice. In this case, the ice cores are recovered from Antarctica, and they go back about 800,000 years in this particular example. Let's start from the 800,000-year-old oldest ice record here. We'll see CO2 rise around 800,000 years ago and then decline. And this is around, say 80 parts per million, this decline. And then a subsequent rise, another decline, a rise. Again, these are all roughly 60, 70 parts per million, these dramatic rises and falls over the last 800,000 years, until we get to the 20th century, where we see a blast off in CO2 in the atmosphere. We've gone up very substantially. Traditionally, over 100,000 year cycles, we see a rise and fall of 70, 80, maybe 100 parts per million. And we see more than that just over the last 150 years as a result of our activity. And it's going to get even more dramatic in the coming years. The three major types of anthropogenic changes that are visible on Earth include chemical. The smelter is emitting sulfur compounds and heavy metals into the atmosphere, and that is devastating to the vegetation surrounding the smelter. And you'll see this all around the world wherever there are smelters. From Flin Flon, Manitoba, Sudbury, Ontario, Trail near Castlegar in British Columbia, to this particular plant on the Norway-Russian border. All of these result in a decrease in population of plants and animals in the region. Physical changes: we've taken away native vegetation and we've established farms. Almost everywhere you look on Earth, you'll see farms, unless you're over the ocean. So this particular image is from Kansas, and it illustrates the influence of irrigation. These are large circular irrigation features that you can observe from an airplane, or in this case from satellite imagery in space. And then the biological effects that people have had on Earth. This is a picture of what is known as a ghost net. These nets are broken loose, they're lost by the fishermen, and they drift around the world ensnaring animals and killing them. In this case, there are a couple of pinnipeds or sea lions that are caught in these nets, and these are air-breathing mammals, so they're caught in a net underwater and they drown in these nets, and they're gradually picked apart by scavengers. So again, these nets drift around the world, killing enormous numbers of animals and leaving their skeletal remains caught in the nets, which is why they're known as ghost nets. This is a very severe problem. Everywhere I've been on Earth, I've seen pollution, and I've seen nets like this in Antarctica on the beach. I've seen nets like this in Greenland on the beach, in Iceland on the beach. Everywhere there's water and people, you'll find fishing gear and junk. The increase in greenhouse gases in the atmosphere since the Industrial Revolution have been driven by fossil fuel burning. That's the most obvious one. This is a coal plant here in operation. Deforestation, also probably obvious if you've driven around the western US or western Canada. You've seen deforestation. If you've certainly been to the tropics, you've seen it. And land use changes. This can be a portion of deforestation, where we convert, in this case, tropical forest, rainforest, to agricultural land. I've put a short video in this module that you can click on about the influence of anthropogenic change on the Earth's surface as viewed from space. It's just about 5 minutes long, so take a look at that when you get a chance. Atmospheric and ice core samples demonstrate the increase in CO2 as well as the increase in methane and nitrous oxide over the past few hundred years. And this is very clear from any data set that you take a look at. In this upper image, we're looking at carbon dioxide. We have a variation in carbon dioxide and CO2 in the atmosphere that occurs naturally. We've subsequently got involved a couple hundred years ago, you can see here, and the net result is a very dramatic, the most dramatic change in CO2 in the last million years. Looking at methane, the same thing. We have a long-term natural trend, and then the short-term post-industrial revolution trend, which is pretty much straight up. Nitrous oxide, another important greenhouse gas. This also rises tremendously or catastrophically at the beginning of the Industrial Revolution. So all of these gases all have negative connotations for us, and they're increasing in the atmosphere because of our activities, recorded in ice cores like this. And basically, we take a core of ice, just like we would take a core of rock, and take very tiny slices of this ice under obviously controlled conditions, and we remove the bubbles from the ice, and we analyze those bubbles to get these gas signatures. Other important chemical changes that we've experienced recently include acidification of the oceans and depletion of the stratospheric ozone layer. We can go back to Climate System Part 2 from minute 2 to minute 4 or so for a review of stratospheric ozone. So I won't go through that in detail again. We will take a closer look at ocean acidification here, though. It starts out with CO2 being released to the atmosphere as a byproduct of fossil fuel consumption, coal, oil, and natural gas indicated here. This CO2 enters the atmosphere. It reaches the surface of the ocean where excess CO2 is going to get absorbed into the ocean. So it enters the ocean. The net chemical drive is from higher concentration here to lower concentration here. That's going to result in this change in acidification around the world. Now, the ocean is chemically complicated. The carbonate system is very complicated and very confusing. We definitely don't have time to cover it in this course. In fact, even in geochemistry courses, it's a big deal to get a handle on how this whole system works. For our purposes, we'll keep it simple. We add CO2 to the atmosphere. It goes into the ocean. It changes the pH by changing the speciation distribution of the carbonate groups here. So the fluctuation between CO2, carbonic acid, to bicarbonate to carbonate are all important for marine species that rely on carbonate. If no action's taken, the impacts are only going to increase. The ocean will not become less acidic. It will only become more acidic unless we take steps to prevent that from happening. It can also be observed in this manner. Here we have CO2 coming from the atmosphere. It's absorbed by the ocean. It goes from atmospheric gaseous CO2 to aqueous CO2 to carbonic acid. This carbonic acid is going to dissociate into carbonate ions and bicarbonate ions. And the distribution of one of these relative to the other is determined by the acidity, or the antilog of the hydronium ion concentration of the solution, which is the pH. So again, for our purposes, adding acids, adding CO2 is going to increase the hydronium ion concentration, increase the acidity of the ocean. That results in greater difficulty for shelled organisms, calcium carbonate shelled organisms, to produce their shells and to maintain their shells. Again, you add acid to limestone, it fizzes and it goes away. You're left with calcium ions and CO2 gas. Same thing's happening here in the ocean, but at a much greater scale. Other types of change include what we've done to the ozone layer. Low-lying ozone forms when sunlight interacts with nitrogen oxides and other chemical wastes. That is our pollution. That's the surface level ozone we call as smog. Stratospheric ozone forms when solar radiation interacts with oxygen, and once formed, it shields the Earth from solar radiation. So solar radiation hits O2 atoms and produces O3 atoms, the triatomic version of oxygen that we call ozone. Now, this ozone is important, as we saw earlier, for blocking dangerous shortwave radiation. It completely blocks UVC, blocks about 95% of UVB, and it blocks a very significant portion of UVA, but not quite enough to protect us completely down here where we live in the smog. We've seen this earlier in the class in that section from climate change, so I won't spend a lot of time on it. Basically, we have an interaction of chlorofluorocarbons, known as CFCs, in the stratosphere that breaks the ozone layer down. The reduction of the use of CFCs due to the Montreal Protocol decreased ozone depletion. Ozone depletion generally occurs during austral winter as ice clouds catalyze the destruction of ozone by chlorine. This is something that has been a problem for a while. We noticed it in the 80s, took steps to mitigate it, and we seem to be making progress, at least in the ozone front. One obvious physical change is that of increased temperature. In the 20th century warming, we see 0.9 degree centigrade increase between the late 19th and early 21st century. Roughly the last 100 years, we've seen a temperature change of about 1 degree centigrade. Another aspect of this physical change, it's not uniform everywhere on Earth. There are places where the Earth is getting substantially warmer, other places where it's getting cooler, although those are limited, and there are places where there doesn't appear to be any significant change. What all of this means is that there is change going on, whether things are getting warmer or cooler, wetter or drier. Those are all change. These temperature anomalies vary over different time scales. That's also important to consider when you're looking at any data set. What's the time scale? What is the change over that time scale? And that's how you get your graph. You get your data to fill the graph. That's how you know someone's telling the truth when you're looking at a data plot. You don't scrunch it all down so it looks like nothing's happening, or blow it up completely so it looks like everything's out of control. Keep everything in perspective. And these diagrams are pretty good at that. So here we see the change in temperature in black, pretty spiky, rapid rises and falls. But in general, you see a trend towards more positive temperatures that coincides pretty well with the trends in increasing CO2 concentration in the atmosphere. So there's a correlation there, that's for sure. Causality is a different story. If we take this back 1,000 years, we can see, again, the 20th century warming is clearly different. It's a standout. It's anomalous compared to climate variation over the rest of the millennium. And we look back over that period of the millennium before we became significant perturbers of the natural world. We see the temperature varies irrespective of changes in CO2. It's when we suddenly ramp up CO2 and start putting a lot of it in the atmosphere that we see a temperature response. Now, when we look at surface temperature anomalies for different periods of time, you can do this for any year of interest to you. 1912, we see a general cooling around the world. And by 1962, we see temperatures rising substantially, here in yellow to orangish. And then by 2012, we see substantial increases in temperature, particularly in the high latitudes, where temperatures have gone up more than a degree, more than 2 degrees in some locations. And in instances where there's significant upwelling, we may see temperatures decrease, but those are always superseded by the increases in temperatures elsewhere. Taking a look here at the temperature departure from average, this is in March 2020, so not too long ago, relative to the 1981 to 2010 base period. Again, climate is everything that happened over a 30-year period in some region of the world. So what we can see standing out is that it's actually gotten cooler here in Western Canada. Isn't that neat? In the eastern and southern United States, much warmer, where it's already too warm. If you haven't been there yet, it's too warm. Over here in westernmost Asia, easternmost Europe, we see substantial increases. And again, the higher the latitude, generally the higher the temperature offset. In this case, the temperature increase. Very limited data for Antarctica, except for the research stations in the peninsula and a few others scattered around the continent. The net takeaway here is that significant regions of the Earth, South America, almost all of South America is warmer. Almost all of the United States and Mexico are warmer. Canada, kind of flipping and flopping. Some parts are warmer, some parts are substantially cooler. Asia and Eastern Europe, much warmer. Africa in general, warmer. Australia, the western half is warmer. The rest of the states are somewhat cooler. Now, when we look at the physical evidence, we have temperature measurements, pretty good measurements going back 150 years. We also have reasonable CO2 measurements going back 150 years, very good CO2 records and very good temperature records going back the last 50 to 70 years. So nonetheless, the 20th century record is clearly anomalous compared to the last few thousand years. The observed patterns of warming are similar to patterns predicted by climate models. So climate models predict that some areas will be warmer, some areas will be cooler, some areas will be wetter, some areas will be drier. That comes out in the models, and it's observed in the real world. So here we have observations, the real temperature variability in black. We have natural forcing from volcanism and solar variability in blue. And you can see there's a separation. It's like the early 1960s, where the natural forcing veers away from what's observed and what is observed when global warming scenarios are taken into consideration. So modeling is presented with this red line here. So the modeled variability is starting to look a lot like the observed variability. That means the models are working. They've been tuned properly and the mathematics are correct. When we look back in time, types of anthropogenic change from the biological perspective have to take into consideration what's happened naturally in the past. There have been a number of mass extinctions that have occurred entirely naturally in Earth's history. A few of them were back in the Precambrian. We won't worry about those right now, the snowball Earth scenarios. Subsequently, we have a number of extinction events. The Hernanchian at the end of the Ordovician is known to be caused by climate change, by glaciation. The end of the Triassic now looks like it was caused by volcanism. CO2 rise at that time. The end Permian extinction, the biggest, baddest, worst case extinction of Earth history that we know of, is believed to be related to volcanism now. Volcanoes erupting under Siberian fossil fuels. These burned up those fossil fuels far faster than even we could do it. And the result was the ocean was acidified. The atmosphere was pumped full of CO2 and methane. The atmosphere was pumped full of smoke from these fossil fuels burning in Siberia. A general global disaster. Environmental conditions during these events would include ocean acidification. We pump the CO2 up in the atmosphere. It goes into the ocean, makes things difficult for marine fauna. 95% of all marine species went extinct at the Permo-Triassic boundary. 76% of marine species went extinct during the end Triassic, early Jurassic extinction. So if both of those were caused by volcanism, those are two mass extinctions caused by elevated CO2. It's now likely that even the Cretaceous Paleogene boundary, that extinction event may have also been driven by volcanism coupled with an asteroid impact. We know there are enormous amounts of basalt emplaced in India at the time, the Deccan Traps, 65 million years ago. So we start punching the climate system with this volcanism, and just for good measure, we lob a giant asteroid into Mexico, into the region near Cancun, to obliterate anything that was surviving the CO2 rise. So in the fifth assessment by the IPCC, this came out in 2014, there's a new one coming out right about now. It was observed that from 1900 to 2012, the Earth's average temperature increased 0.9 degrees centigrade. Most of the warming was caused by anthropogenic increases in greenhouse gases. Greenhouse gases will continue to increase in the atmosphere in their concentration. These increasing greenhouse gases will play a significant role in warming the atmosphere over the next few centuries, maybe over the next few millennia. Now, in the modern world, we've talked about some of these things, CO2 sources and sinks. At the end of the Triassic, we have the splitting open of the Atlantic Ocean, continued splitting of the Atlantic Ocean, and the generation of enormous amounts of magma. Coupled with this magma is degassing of CO2. This is going to result in sucking the oxygen out of deep seawater, resulting in anoxia, so death of the deep waters. This is going to kill off any organisms that live just a little bit below the surface, which is most of the volume of the oceans.